So, welcome to this course on mechanical operations. In the last few lectures, we have been talking about a method of mechanical separation which is based on filtration. And so, we have looked particularly at leaf filters that are widely used in industry to separate large concentrations of particles from fluid streams. So, today I will just briefly talk about another method of filtration which is centrifugal filtration. Centrifugal filters are used particularly when you need to provide an additional mechanism or force in order to cause the separation of particles to happen. Centrifugal filters can be used both for separation of particles from gases as well as from liquids. They rely upon the fact that particles of different sizes and masses will be accelerated to different extents when you subject them to a centrifugal field. By the way, we have one equipment in our mechanical operations laboratory called the air classifier, which is actually a good illustration of how this method works. So, you introduce a fluid stream. The air classifier of course is for gases which has particles entrained in it, and then you set up a centrifugal field inside the equipment using a rotary wheel or some such method, and as the dust laden gas is introduced into the classifier, the particles are blown to the outer periphery. So, the particles tend to collect at the walls and then slowly roll down the sides of the walls, whereas the gas basically stays in the center and exits upwards. So, that is basically the principle of how a centrifugal classifier works. Now, the ratio of the centrifugal force to the gravitational force, which is mv squared by r divided by mg, is called the separation factor, and the higher this factor is, the greater will be the effectiveness of the separation. So, typically air classifiers work well for large particles because they tend to get accelerated to greater velocities, and it is possible to effect a very clear separation of particles from the fluid that they are suspended in. Certainly the centrifugal field or the RPM plays a role as well. In fact, one of the parameters we used to offer air classifier as an experiment in the mechanical operations lab. I do not think we do that anymore, but one of the key parameters that the students would vary is the RPM to look at the effect that has on separation efficiency for various particle sizes. So, there are a few parameters that you can control in a centrifugal separator. Centrifugal fields enable you basically to achieve the same separation in less time. So, you save on process time. In terms of energy consumption, they are a little more energy intensive because you do have to set up the centrifugal field, and that typically requires some investment of mechanical / electrical energy to happen. But especially in industries where you are looking for a very clear separation, centrifugal fields are used because they just make the separation process more efficient, more effective, more clear cut. There is less overlap of fractions that you are trying to separate. So, it has all these benefits. It is also a good technique to use when you have particles that are very similar in size, but differing in density that you want to separate. Classic example is rice husk. When you dehusk rice, the husk part and the rice kernel are approximately the same size, but clearly they are of very different densities. And a classic problem in rice husking mills is how do you separate the rice from the husk, and these types of centrifugal classifiers work extremely well for that purpose. So, centrifugal filtration is sort of a niche process, and because it does involve more capital equipment, possibly more operating cost and so on, but it is used where that increased effectiveness of separation is desired. Okay, now the reason that we need separators is because very frequently we encounter process fluids that have suspended particles or chemicals that need to be removed. The end product that you are interested in may be the clean fluid, or it may be the suspended phase that is of commercial interest, but in either case you need the separation to happen. Another instance where you need size wise separation and classification is when you are trying to do size reduction operations. Size reduction is also known as comminution. It is widely used in many industries because typically the raw material comes to you in a form that is not usable in the process. It comes to you in the form of, for example, in mineral processing, the ores that are mined come in huge boulder sizes, which need to be slowly size reduced to a size where they can be used in a process like in a power plant or in a combustor and so on. Any raw material that you use, whether it is in the power industry or whether it is in chemical manufacturing or in pharma, the initial size of the raw material is unlikely to be in the range that you are interested in. Now, very infrequently you have the other problem that the raw material is a very fine size and you actually have to grow it to a larger size in order to use in your process. But more typically the raw material will tend to be of a larger size than required, so you have to do size reduction. So, when you talk about size reduction, there are 4 classical techniques. First is compression, second is impact, third is cutting, and the fourth is attrition. Compression, as the name suggests, uses a compressive force to break down particles. Good example is a nut cracker. If you ever seen one in operation, you hold the nut between 2 faces and apply a compressive force to cause the nut to fragment, right. Cutting, of course, all of you are familiar with. You take a scissors and you can cut a paper to much smaller sizes. So, that is a size reduction that you are achieving by cutting operation. Impact, again, anytime you swing a hammer and you break something to smaller sizes, that is size reduction by impact force. The fourth type, attrition, is where you are essentially using more gradual forces, typically an abrasive force, in order to have the size reduction happen. Now, attrition happens, as I said, more gradually and over a period of time, and it is also used as a second stage size reduction process after primary size reduction has been achieved by typically by compression and impact. Crushers and grinders are the workhorses of the size reduction industry. Crushers again are used as the primary stage to reduce raw material to a manageable size, and then a grinder is used to take particles that have been size reduced to a even finer size. So, a crusher could typically produce as output centimeter sized or millimeter sized particles, whereas a grinder can take these particles and reduce them to millimeter size and micron sizes. There are also what are known as ultrafine grinders, which can take particles in the micron sizes and reduce them to submicron and nano sizes. So, if your end product has to be, for example, in a submicron range, you need a sequence of size reduction equipment. Start with a crusher, go to a grinder, go to an ultrafine grinder, and typically there also needs to be a classifier that can help you separate out particles in various size ranges for use downstream in your process. So, what are some requirements, or what would an ideal size reduction system look like? It has to have large capacity, because we are talking about industry use. So, it is not enough if whatever equipment or process you have can only process a few milligrams a day. It has to be able to do tons of material per minute in some applications. So, these have to be scalable, they have to be able to handle large quantities of material. At the same time, the energy usage has to be minimized. The key metric is how much energy needs to be input in order to create a new unit surface by size reduction. every time you do size reduction, you are actually creating surface area, because for the same volume of material, if you break down to smaller sizes, the total area, surface area increases. So, size reduction involves creation of new surface, and one of the key metrics that process engineers need to look at is how much energy does it take for me to create unit new surface. The third metric that you need to look at is, for a given feed size distribution, what is the product size distribution that I require, and can the equipment meet that? Because ultimately the use of a size reduction equipment is to reduce size, but you have to remember that the feed is not of uniform size. There will be a size distribution in the feed, and similarly there will be a size distribution in the product, and most size reduction equipment do not try to control the minimum size. What they try to control is the maximum size. So, a size reducer like a crusher will be rated based upon the maximum size that it will allow. You know, this crusher can give you, let us say, 2 millimeter output. It does not mean that all particles coming out of it are going to be 2 microns in 2 millimeters in size. It means that the particles will be 2 millimeters or less. So, there is no, typically there is no control over the minimum size that a size reduction equipment can produce. Maybe okay in many cases, but there may be instances where you also care about the minimum size and you want to optimize your size reduction process so that the size distribution is in a certain range where you specify both the maximum size as well as the minimum size. Now, if you look at industry, I told you about the ideal requirements. Very few equipment really meet all these requirements for ideal operation. There is a huge gap, and so there is a lot of opportunity certainly for process engineers to work on size reduction equipment and try to improve their effectiveness and their efficiency and so on. But it is an opportunity that is difficult to take advantage of, because size reduction for the most part is not a theoretically simulatable process. Size reduction tends to happen somewhat I would say in a random or empirical fashion. There are very few theories of size reduction. What you have are empirical correlations based on a lot of experiments being conducted and data being taken. The problem with experimental correlations is that they may be valid for the range of parameters under which you did your experiment, but you cannot extrapolate and sometimes you cannot interpolate either. So, any model that you develop purely based on experimental data is always of questionable value. You are never sure that the next data that you take is going to match what you have developed as a model based on previous data. That is the advantage of a theory based model. If you have a model that is based in theory, where you have understood the mechanism involved and you have developed a predictive model based on mechanistic understanding, then you can have a fairly high level of confidence that the next set of data that you take will also match the first set of data, but you never have that assurance when you develop a model based on experiments. And that is what again makes the whole job of a process engineer very challenging. When you are trying to work with size reduction processes, you are trying to achieve the results that you need for your process, and at the same time you are being told to reduce energy consumption, you are being told to increase capacity, and there is no way you can predict how changes in your operating parameters or in your feed parameters are going to change your output. So, it is a tricky challenge. Now, the energy efficiency can be modeled or can be represented as a new surface created divided by energy absorbed by the material. That is a fairly simplistic way of defining the energy efficiency. But in this definition, it is very important for you to keep track of the size distribution that you achieve, because the total area that is created, you have to know the different sizes of particles in the product and their representative numbers and surface areas, and you have to cumulatively estimate the new surface. So, you have to know the total surface area of your feed particles and the total surface area of your product particles. The difference between the two gives you the net creation of surface, and you divide it by the energy input. That gives you an idea about energy efficiency. But a more useful way to look at this is in terms of the surface energy parameter that we had discussed previously. You can also define, for example, in a crusher, the crushing efficiency eta C as surface energy created divided by energy absorbed. It is a better definition because it is non-dimensional, gives you a number that you can work with. Why is surface energy created? You have to look at the process by which fragmentation happens. When you supply energy to break down a material, what happens? First, the particle actually gets distorted. It does not fragment right away. It gets distorted, strain gets built in, or stress. The actual fragmentation only happens when the distortion exceeds the ultimate strength of the material. So, up to a certain point, you just keep building up more and more stress in the particle. The stress gets released as work when finally the fragmentation happens. However, there is a lot of excess energy in this process. Not all the energy that you transfer to the material is getting used up in fragmentation. The excess energy is used up in two ways. One is as heat. You will notice that whenever size reduction happens, there is an associated rise in temperature. So, some of the energy that you have imparted to the material in order for size reduction to happen gets translated into thermal energy. The residual energy is stored on the newly created surface as added surface energy. So, if you do a surface energy measurement of a particle before and after size reduction, you will see that there is always an increase in the surface energy after the fragmentation process, and that is the reason why re-agglomeration or aggregation is an issue with many size reduction processes, because as we have seen before, an increase in surface energy results in an increase in particle to particle cohesion, particle to surface adhesion, and so on. So, this increase in surface energy is normally not a desirable thing, but it happens anyway. So, again, from a process engineer viewpoint, what you should try to make sure is as much of the input energy is used up in the fragmentation as possible, and as little is wasted as either surface energy buildup or as heat release. So, if you use this definition, you can define a parameter ES, which is surface energy per unit area, then you can write this as ES times total area of the product minus total area of the feed, and you divide it by, let us call it Wn, which is the net energy that is supplied to the material in order for size reduction to happen. But there is a second efficiency called the mechanical efficiency. It is called that eta m, which is equal to this energy absorbed divided by energy input or energy supplied. So, this is Wn over W. But W is really what you can control. It is the total energy that you are supplying to the system. So, how do you can now go ahead and write that W as being equal to ES times AP minus AF divided by eta M times eta C. The efficiencies in crushing, by the way, tend to be extremely low. I mean, it is not that it is 50% or 60%, we are talking about 1 to 2% efficiencies. So, size reduction through mechanical means is one of the most inefficient operations you can imagine. So much of the energy that you are inputting is just going as waste, okay? And that is why obviously there is a lot to be gained. In many of the processing industries, from cement to power plants, a lot of focus is given to optimizing the operation of the size reduction systems, because that is where a substantial amount of the energy usage goes in the factory. So, if you take this W and let us say that you have a feed rate of some T tons per minute, you can get the power that you require as a multiple of the work done times the feed rate, and that is going to be your rating for the equipment that you use to perform your size reduction operation. So, how do you minimize that power? You have to look at each of these values, and you should try to maximize the denominator and minimize the numerator. Now, this difference obviously you want to keep it as high as possible. I mean, the whole idea in size reduction is to have a much finer product compared to the feed. So, you try to maximize the term within the parenthesis, you try to maximize this, you try to maximize this. So, the only in the numerator, again the surface energy is the one term that you can have have some control over. You should try to design your process so that the material absorbs as little surface energy as possible. It is going to help you with your power consumption, and it is also going to help you with minimizing any aggregation or formation of clumps of particles rather than individual or separated particles. So, if you look at size reduction as an operation, the key thing that you are interested in is what is the differential amount of energy that you need to input in order to get a particular size reduction. And this is the general law that has been formulated to describe how size reduction happens with input of energy. So, dE is your differential input of energy, C is a constant, x is the size of the particle, n is an exponent. So, if you solve this, if you integrate this, you get E equals minus C over n minus 1 divided by 1 over xp to the power n minus 1 minus 1 over xf to the power n minus 1. So, this is the general formulation of the size reduction equation for a given energy input. However, there are special cases of this that are of interest to us, and by the way, this only applies when n is greater than 1. When n equals 1, you go back to this equation and solve it, you will get E equals C k times logarithm of x f over x p, where C k is a constant. This law is called Kix Law. So, the Kix Law says that the energy required to do size reduction goes as the logarithm of the sizes. An empirical law, as I said, there is really no good theoretical basis to any of these laws. When n is taken as 1.5, you get something called Bond's law, which says E equals C B times 1 over x p to the power 0.5 minus 1 over x f to the power 0.5. So, it basically says the energy required to reduce from one size to another goes as the square root of the size. When n is equal to 2, we get something called Rittinger's law. Obviously, that goes as E equals C r times 1 over x p minus 1 over x f. So, these are special cases of the energy law or size reduction law. What is the physical implication of these laws? The first thing that you will realize looking at these laws is that the size reduction efficiency or the energy required obviously in all these laws is related to a mean size after size reduction and a mean size before size reduction. And by the way that the mean sizes are defined is different in these laws. For example, the Rittinger law, if you state it in words, basically says that the work involved in size reduction is proportional to the new surface that is created. Okay. So, that is a very simple statement. It says if you want to create more new surface, you do more work. Rittinger's law does not take into account the fact that different particle sizes require different energies to break down. So, to break down from 100 microns to 10 microns, the energy input that you require is going to be very different than the energy that is required to break down from 10 microns to 1 micron, right. By the way, in your mechanical operations lab, you will do this experiment where you will use a ball mill to do size reduction. You will track the size, product size as a function of energy input, and you will actually compare your data with these laws to see which one is the best simulation of your experimental data. So, hopefully, you will draw some conclusions at that time regarding the validity of some of these laws. So, in case of Rittinger's law, the relevant x bar is summation ni xi cubed over summation ni xi squared. So, volume to surface mean diameter is taken because there is no single diameter, right. You will again remember that the feed will have a size distribution and the product will have a size distribution. So, these techniques rely upon defining a certain mean size and basing the energy requirements on that mean size. Even that approach has a lot of pitfalls. As you can imagine, the same mean size can be achieved with a very different particle size distribution, and you would expect that the size distribution should have an effect on or should have an influence on the energy input, not just the mean size. But again, these are very simplistic definitions that are like, I do not know, 50, 60 years old, maybe even older, and they do serve a purpose. I mean, if you look at your data that you will get from your own experiments, you will find that there is a pretty good fit to what these laws are predicting. At least you should be able to, typically the exponent you will get clearly will be somewhere between 1 to 2. When you actually do the experiment, because that is a range in which scientists who have done this for many years have kind of established n equals 1 to n equals 2 as a range in the energy efficiency law for size reduction. So, you should expect your data to kind of match that. In the case of Bond's law, the Bond law basically says that the work required to reduce a large feed to a particular product size goes as the difference in the square root of the mean diameter, but what he's really saying is the critical parameter here is the square root of SP by Vp, that is the specific surface area of the particle. So, his Bond's take on this is that the energy required is proportional to the square root of the change in the specific surface area. So, when you do it that way, automatically you come up with a square root dependence on particle size, and here the mean diameter is again going to be 1 over your x bar is going to be equal to summation of SP to summation of Vp, which is essentially the same as our previous definition. So, both the Rittinger's law and the Bond's law pretty much use the same definition of particle size, of mean particle size, but they postulate a different exponent in the dependency term. Bond's law also introduced something called a work index, which is related to this constant. By the way, the Ck, Cb and Cr are the respective constants for the different laws, and they are not really relatable to each other, and Ck and Cr are completely empirical constants that you have to derive based on your own experiment. They have the statement that has been made, in fact, by all three, Kix, Bond and Rittinger, is that the constants depend on many things. They depend on the material, they depend on the method by which the size reduction is happening, they depend on not just the bulk properties of the material, but even the surface finish, roughness, other properties of the material. So, they are in that sense totally empirical constants. However, Bond went one step further and he related Cb to something called the work index. He said that Cb equals 1.43 times work index, where work index is defined as the work that it takes to take extremely large feed, theoretical size of infinity feed, and break it down to a product size such that 80% of the product can go through a 100 micron screen. Okay. So, the key numbers here are 80% of product must go through 100 micron mesh. So, Wi is the work required to make that happen, and then once you have Wi, you can estimate Cb and plug it into this equation. Now, the thing again you will see in these expressions is that they don't really hypothesize a dependence on the actual sizes. In other words, suppose you did this and you calculated E, say as a function of xf over xp, you will get some dependence, right? As the product size decreases for a given feed size, the energy will keep increasing. The energy that is required to make that happen will keep increasing. But the thing is, this xf by xp is not, I mean it's considered a unique parameter in this equation. For as I was saying, this xf by xp, let us say some value of 10, this could represent 100 microns by 10 microns, or it could represent 1 millimeter by 100 micrometer. So, particular value of xf and x divided by xp can be achieved by many values of xf and xp. And is it always true that you will always require the same energy input? Obviously not. I am sure you can intuitively feel that if you take a large particle, it is much easier to fragment it to smaller particles, and if you take a very fine particle and try to fragment it further. So, clearly these curves are not unique. In fact, the energy requirement will keep going up as xf increases, the energy requirement will increase. As XF decreases, the energy requirement to create unit surface area will keep increasing, whereas as the feed particle size increases, it will take less energy to break it down. So, you have to be careful with your understanding and application of these laws, in the sense that the energy required to create new surface keeps increasing as the surface becomes smaller and smaller. That is a key thing that you have to realize in size reduction by mechanical means. It takes a lot more work to break down particles to finer sizes as you keep proceeding with your size reduction. This is again you will observe when you do the experiments in the mechanical operations lab. It becomes progressively more difficult to effect a size reduction as the sizes get smaller and smaller. And this is true about size reduction operations that are based on impact, that are based on compression, that are based on cutting, and that are based on attrition. There are very few size reduction operations, mechanical size reduction operations, where this principle is violated. One of the techniques, in fact we talked about that a little bit in one of the earlier classes, where we use acoustic energy as a way of reducing size. In that case, what you are relying upon is a direct interaction of a shock wave with the material whose size you are reducing, and that technique, because it relies upon the interaction of an imploding bubble with the particle that is in suspension, is much less size sensitive compared to methods such as ball milling. And in fact, I think I showed you a graph in that lecture that showed the energy efficiency comparison between ball milling and cavitational size reduction. The only size reduction technique where you can try to avoid the penalty that you pay in terms of increased energy input to get more surface is one that is based on an acoustic field. So, there is a lot of interest in industry in using again a sequence, crushers for the reducing large particles to smaller sizes, grinders to reduce them further, followed by ultrafine grinders to do a further size reduction, and finally something like a cavitational size reducer, which will take it down from micron sizes to sub-micron sizes. So, you have to kind of look at this whole thing as a system to go from your feed size to the ultimate product size that you are interested. So, if you look at industry, there are many types of size reduction equipment that are employed. In each of the categories that we have mentioned, you can subclassify them. For example, you have crushers, and there are impact crushers, there are roll crushers, or if you are talking about grinders, there are compression grinders, there are attritional grinders, there are rotational grinders. What we will do in the next class is kind of talk a little bit about the different types of size reduction equipment that are used in industry, which will give you a kind of an overview of how size reduction is done, and after that we will come back and discuss in more detail this whole concept of new surface creation and how that can be related to the energy that is being input into the system. Most of our discussion will focus on ball mill because of all the grinding techniques that are used in industry. Ball mills are the most widely used, so we will spend a little bit of time talking about ball mills in more detail. Any questions on what we have covered today? Yeah.
Can you once again explain the graph with EA,
Yeah, see the whole question is this a unique line, or does this line shift up and down based on the actual values of XF and XP? If you make the argument that there is only one line and it does not matter what XF and XP are individually, what matters is only the ratio, then obviously there will be only one line, but in reality that is not true. In reality, the actual values of XF and XP also have an influence, it is not just the ratio, right, and that is where we will discuss that in more detail. So, as XF becomes smaller, for the same ratio of XF to XP, the energy required will be much greater. Okay?
This eta C term, energy created by energy.
Yeah.
Should that be ideally very low so that most of the energy spent is used for the cell destruction?
But when you say a surface energy created, that's also proportional to surface created. So if you minimize that, you are also minimizing how much. So the trick is to create surface but minimize residual energy.
Yeah. The surface energy is the residual energy.
Right. So
the constant of proportionality should be reduced.
Yeah. See, when you look at surface energy, there are two components to it. There's one is the surface energy increase associated with the increase in total area, and the other is surface energy increase per unit area because of excess energy built up. So it's a second parameter has to be minimized, but the first parameter should be maximized. Okay, see you next class.